Hey everybody, this is Mr. Piercy. What we're going to be looking at in this video is how we're going to use proofs to show why a statement is true. The main way that we show statements to be true, meaning that how we write a proof of something, the main way that we do it in geometry is actually with something known as a two-column proof. A two-column proof is something that it looks exactly like what it sounds like. It is two columns where on the left side of the table or proof that we're making are the statements that we're using in a logical order, meaning that we progress from one statement to the next in a reasonable manner. And we, on the right side, are the reasons for those statements. What you see in the image is just a very basic, kind of two-column proof that says we have some given information and we want to prove why something is true. Okay, so a proof generally is going to be just some kind of a logical way of demonstrating why something is true. Usually, we don't use two-column proofs in, our daily lives. If you have to show why, something is true or not true, usually what we do is we just explain it using words. If we were to write those words down, we would classify that as a paragraph proof. But a lot of times what we use in geometry is the two-column proof that you see here. The last thing that we're talking about is theorems. Well, we have several types of statements that we use in geometry. A postulate is a statement I can accept as true without having to explain why it's true. A conjecture is a statement that I make based off of a pattern that I see, and the pattern can be, or the statement that we make, the conjecture, could be a true conjecture or a false conjecture, depending on what we see, how we test it. And a theorem is a statement that usually is going to be true, but you have to explain why it's true. You have to prove it to me. You can't just, it's not one of those things that I can just accept to be true like I can in a postulate. So what it's asking us to do here, it says, well, can you write a two-column proof? Can you work your way through it? Can you go through the logical progression of statement, reason, statement, reason, statement, reason? Some students are going to be wonderful at doing stuff like this because they're mentally, I don't want to say developed, but mentally they're more wired to have kind of a sequential way of thinking where we say is very structured, it's very ordered. And some students struggle with it a little bit. They just need some practice with doing two-column proofs, and usually then they start doing okay. And unfortunately, some geometry students, at the time that they take geometry, they're just not quite ready for the thinking of the structural nature that we use in a two-column proof. And those students usually do have a difficult time working through them. Okay, but most students, regardless of their skill level, will get better with practice. So let's start with this one. In the instructions it says use a diagram to prove that the measurement of angle 1 is equal to the measurement of angle 4. Because that's what we're being asked to prove. What we are asked to prove, this is always going to be the very last statement that we have. Whatever we're asked to prove is always going to be whatever our last statement is. And almost always, I won't say always, but almost always, the information that's given to us is usually going to be the first thing that we have. So if you notice, the statement in row 1 says that the measurement of angle AXE and the, oops, don't want to draw through it, and the measurement of angle AXD, that statement is given to us. So right away we're starting with information that's given to us, which is very common in a two-column proof. Very nearly always, the very first statement is going to be something that was given to us. Now, if you notice, there's more information that's given to us, but it doesn't make sense sequentially to include that at the beginning. So we're going to include that later on, and you can see that's going to be in step 5, but I don't want to get ahead of myself here. So starting off, we know that the measurement of angle AXC and AXD are congruent to each other because that was given to you. So now we're going to move on. Well, the measurement of angle AXD is going to be made up of two other angles, in this case angle 1 and angle 2. If I take the sum of those two, I get angle AXD. That's recognized as the angle addition postulate, saying if I add two angles together, I get another bigger angle. Same thing with angle AXC. Angle AXC is the sum of angle 3 and angle 4. So we use the same reason for both statements. Well, if AXC is equal to AXD, then that means that the sum of angle 1 and angle 2 must equal the sum of angle 3 and angle 4. And so the reason that we use that, or the reason that we give for that statement, is that's the substitution property of equality. If these two things add together to equal these two things, or if this angle is equal to this angle, and the first angle is made up of these two angles, and the second angle is made up of these two angles, then it means that the sum, whatever those two angles that we add together, have to be the same because the original angles were congruent to each other. So now moving on to step 5, here's where we're going to use the fact that the measurement of angle 2 and the measurement of angle 3 was given to us. And I know that was given to us whether it's because it was told in the original information where it actually says the measurement of angle 2 is equal to the measurement of angle 3, but I also know that they're giving me that information because of the congruent symbols showing me in the diagram that angle 2 and angle 3 are congruent to each other. Well, the next progression is that, well, the measurement of angle 1 and the measurement of angle 3 are equal to the measurement of angle 3 plus the measurement of angle 4, because if 1 plus 2 is equal to 3 plus 4, and 2 is equal to 3, then I can say that 1 plus 3 is equal to 3 plus 4 also. Again, we're using substitution to show that. So algebraically, if we were to solve, if we were to move the measurement of angle 1, or I'm sorry, the measurement of angle 3 from one side of the equation to the other, then the measurements of angle 3 would cancel out of the equation that we see in step 6, leaving me with the statement the measurement of angle 1 is equal to the measurement of angle 4, which is what we're trying to prove. And what I did to get to that last step was I used the subtraction property. And so that would be our complete proof justifying the statement that the measurement of angle 1 is equal to the measurement of angle 4 in this particular diagram. So in a previous video, in a previous section of notes that we would have taken in class, we talked about the properties of equality, and we saw a property of equality used in the last example. We used the substitution or the subtraction property of equality and the substitution property of equality. Well, not only can we use those terms, substitution, but we also had the reflexive property of congruence, the transitive property, I'm sorry, of equality, but not only do they work for equality statements where I say something equals something else, but they also work for congruence statements as well. So before, where I had the reflexive, symmetric, and transitive property of equality, well, I also have those same properties in with my congruent statements. So at this point, go ahead and pause the video and answer example number 2 on your own. Shouldn't take very long. See which of the properties that you see here, reflexive, symmetric, or transitive, match what you see in example number 2. When you're done, hit play again and come back and see what your answer looks with mine. Okay, so hopefully we have some good statements here, or you have a good answer, I should say. Name the property illustrated. Well, what we're noticing is that we're just taking the same statement and we're reversing the order. Instead of saying angle 5 is congruent to angle 3, we're turning it around to say that angle 3 is congruent to angle 5, and that's exactly what we see in the symmetric property of congruence. Now, whether we say the symmetric property of congruent angles or whatever, if we say congruent angles, we're being very specific, which is fine. But generally, if you recognize we're taking the same statement and just turning it around, that is symmetrical. So the symmetric property of congruence in this case. Well, here in checkpoint 1 and 2, again, go ahead and pause the video and answer these questions as best you can. And when you're ready, go ahead and hit play and come back so you can see how your answers look compared to mine. All right. Ideally, again, you have some good answers for the fill-in-the-blank stuff of our two-column proof. It's a very, very straightforward, simple two-column proof. And question number 2, again, what property are you seeing illustrated by the statements? So looking at the proof, the first statement that we have is that BC and AB are the same. Well, that's given to you. Pretty much everything is, the first statement is going to be given to you, or the reason is given to you. So the second statement says that AC is the sum of AB plus BC. Well, looking at that, we're just talking about segment addition. Well, if AC is equal to AB plus BC, and that BC, it was given to me that BC was equal to AB, then I can substitute AB for BC in step 3 and show that AC is equal to AB plus AB, which is what we were asked to prove. So all we did was substitute on that last step, and we're done with our proof. Here, looking at the properties that we're illustrating, if I'm saying that angle T is congruent to angle H, and I'm also saying that angle T is congruent to angle B, then I can conclude that angle H is congruent to angle B, and that would be known as the transitive property of congruence, very similar to the law of syllogism that we have for our laws of logic. So here we are just moving on with doing a little bit more practice with some two-column proofs. Here we're using properties of equality to show something is going to equal something else. So the statement that we're given says that ray BD is going to bisect angle ABC, and we want to prove that the measurement of angle ABC is equal to 2 times the measurement of angle 1. Now, off to the side it says before doing your proof, it's very good to draw a diagram, because here in this example we're given a diagram, but we don't have to be given a diagram. We can just say this is your given information, prove this statement. If it's not giving you a diagram, it's a really good idea to draw a diagram based on what it's telling you. So you could just draw some generic angle ABC and then draw a ray BD in it to bisect it, making one of them angle 1, one of them angle 2. So anyway, ray BD bisects angle ABC. That's given to you. Now the next statement is what's not, we don't know that. But looking at the reason, okay, the reason it can be a clue to be what the next statement is. But remember, the statements really should be in kind of a sequential logic, or a logically sequential order. So if I bisect an angle, then it means that I'm going to be left with 2 angles that are congruent to each other. And according to the definition that we see the definition of an angle bisector shows that we have to have 2 angles that are congruent to each other. Whether you call it angle 1 or angle 2, or you actually name them angle ABD and CBD, it doesn't make a difference, as long as you recognize that we have those angles that will be equal to each other, or congruent, I should say. So here, looking at step 3, again, we need to show that angles are going to be equal to each other in some way. Well, if I bisect something, not only are the angles congruent to each other, but the angles must be equal to each other in measure. So angle 1 is equal to angle 2. Or you could have said ABD and CBD again, but I just didn't want to type them all out. Now, looking at the next step, in step 4, it says angle 1 and angle 2 added together equal angle ABC. Well, that's a clear example of using angle addition. So we call that the angle addition postulate. And since angle 1 and angle 2 have the same measurement in the equation that's listed in step 4, I can replace angle 1, I can replace angle 2 with angle 1 again to show that because they're equal to each other, I can substitute one of them for the other in the equation. Well, if I simplify that, I'm going to get 2 times the measure of angle 1. So because those are like terms, we're going to get 2 times the measure of angle 1 to be equal to the measurement of angle ABC. And here, the statement that or the reason that they're giving is the distributive property of equality. I'm really not 100% sure I agree with the distributive property of equality. I would probably simply say combine like terms for that, or well, I wouldn't want to say the addition property of equality, because addition property of equality implies that we're moving something across the equal sign, but I would probably say just something like combine like terms, because the distributive property implies that we're multiplying something into parentheses, and I don't really care for that last state or last reason, but you know, it is what it is. The authors gave it to us, so we'll use it. So here, where we're talking about how we write a two-column proof, keep in mind it should be a logically sequential set of statements where we start with something and then we go from that one to the next one to the next one until ultimately we reach our conclusion proving the indicated statement. So here in the concept summary that we have, we want to write a two-column proof. Again, 99% of the time probably we're going to start with information that's given to us. I know that AB is congruent to CD because it was given to me. Well, if they're if they're congruent to each other, then that means they must have equal lengths. So that's the definition of what congruent segments are, is that they have to have the same length. Well, if AB is congruent to CD, then that means that CD must also be congruent to AB. So their lengths are equal to each other. That's the symmetric property of equality where we're just turning them around. This is one of the rare cases where we actually see that. You usually don't see the symmetric property of equality used very much. And so that's how we would finish filling in, you know, the two-column proof that we see here for the statement that we were asked to prove. Now this is a much more appropriate kind of two-column proof. It's giving you a situation, but even though here it's giving you a situation, most of the time what we'll see as a geometry student is you'll see something dealing with a figure of some kind, whether it's angles or segments or triangles or some other kind of polygon, or even a property about that polygon. But a lot of times what they don't give you is a diagram for it. They just say we have this thing, and you're having to rely on your knowledge of your vocabulary in order to be able to say, oh, well, this means this, and I can draw it this way, and so on. So even though this isn't giving you a diagram to work with, it's a very good example of the kind of two-column proof that you may be expected to do. So it tells you, go ahead and read the example for yourselves, and I know you guys know how to read, but since the diagram isn't given to you, it helps if you draw a diagram of some kind. And so I know we're, you know, along a line, we have a rest area, an exit, and another rest area, based on the information that was given to me in the problem. Also given to me in the problem, because it's telling me that the distance between the Rice exit is halfway between rest area A and the Mason exit, I can show that we have congruent segments somewhere. So we have what I have shown for you here. Well, the proof that we're asked to do is to prove that point M is the midpoint of segment RB. Well, taking the information that's given to me, we're going to say R is the midpoint of AM and that MB is equal to AR. So you can see in the first statement, we're actually combining both of those at the same time, so that way we don't have to write it down twice. You know, put one in as a given and put the other one as a given. They're both given, so we can combine them into one statement. Well, based on the fact that R is the midpoint of AM, we can use that information to show that AR must be congruent to RM, because that's the definition of what a midpoint does, divides it into congruent segments. Well, if AR is congruent to RM because that's the definition of what a midpoint is, we can move on and say that AR must equal RM because that's the definition of what congruent segments does. Not only are they congruent, they must have the same measurement. Well, now we can look and say, well, now that we know that the measurements of those things have to be the same, the segment from MB to RM, those have to be equal to each other, and the reason why, in this case, would be the transitive property of congruence. So if you notice, again, kind of up here at the top, it tells you MB is equal to AR. Here it's telling you, and so what we're showing is that AR is equal to RM, so we're coming here to show that this is equal to RM. So that means now I can take the RM and substitute it for the AR because that's the transitive property of equality. Well, again, now we're moving back down. So if those two segments are equal to each other, not only must they be equal to each other, but they must also be congruent to each other because that's the definition of what congruent segments is. And so that means that M has to be the midpoint of the segment because that's what the definition of a midpoint is. So we have proven that M is the midpoint of RB. And again, the statement that we're given to prove really needs to be the very last statement that you do. So lastly here, go ahead and try answering this question. In example 4, we have rumble strips at these locations. So what other rumble strips have to be the same distance away from something? So go ahead and pause the video here, go back to the diagram if you need to, answer your question, and once you have an answer, go ahead and hit play again and check how your answer looks with mine. All right, so last question here. Hopefully we have some good answers to look at. In example 4, there are rumble strips halfway between Rice and Mason. What other two places have to be the same distance from the rumble strips? Oh, well, it helps if I have my pointer on. Well, rest area A and B have to be the same distance away from the rumble strips also, because we were able to establish that all of those segments were congruent to each other and where the midpoints were. That's going to take care of this video, ladies and gentlemen, where we're practicing doing two-column proofs. It can be a little intimidating at first, but we will be practicing them more throughout the curriculum. But if you have any questions about what you've seen here, by all means, let me know what they are, and I'll be happy to help you out. Until next time, ladies and gentlemen, thanks for watching and take care.